Hi, I'm Kemil and this is Chem with Chem. Now, this is an adaptation of an online lesson or an online session where we actually did the work through for a worksheet on structure and bonding and mole concept, mole conversion. I mean, what a combination. We converted from moles to mass, mass to moles, number of particles to moles. So feel free to check slide to the part that you prefer. Of course, if this is your first time, welcome to the channel. Consider subscribing, check out the different content that is here. And of course, be sure to leave a like and leave feedback. All right.
So we're just going to run through, and this is a video so you can slow down, pause, um, go back as many times as you wish. There shouldn't be any issues with this, but I'll try to be as clear as possible and go as in-depth as possible. So here we're at number one, to predict the type of bonding that will occur in the following pairs of atoms. So we should be thinking ionic or covalent, depending on if we are seeing a metal and a non-metal bonding. So sodium and fluorine, we have a metal and a non-metal. So we know this would be ionic. Oxygen and chlorine, those are two non-metals. So that would be covalent. Phosphorus and chlorine, also they are two non-metal elements. So that would be covalent. Aluminum and oxygen, metal and a non-metal. So that would be ionic. Sulfur and oxygen in the same group, group 6, those are two non-metals. So those would, the bonding there would be covalent. Number 2, identify this type of structure which exists in a solid. X, which has a high melting point, never conducts electricity. So let's look at those keywords. X has a high melting point. So we're talking about strong forces of attraction. It never conducts electricity. So once it never conducts electricity, we should rule out metallic structure, because a metal would conduct electricity. And the fact that it is insoluble, it does not dissolve in any solvent at all, tells us that we would have to rule out ionic as well. We're ruling out simple covalent or simple molecular. From we hear the term high melting point, we're ruling out. So these are the type of structure that we have. We have metallic, the structure of solids. We have metallic, we have ionic, we have giant covalent, and we have simple covalent. When you hear that this structure X has a high melting point, we're ruling out simple covalent, because simple covalent compounds have low melting point. When we hear never conducts electricity, we're ruling out metallic. And when we hear that it is insoluble in all solvents, we are ruling out ionic, because we know that ionic solids are soluble in water. So that would leave us with giant covalent. So that makes X giant covalent. All right. So let us look at what Y would be. Let us look at Y. So again, the four structures that we could have, they are the same: metallic, ionic, giant covalent, simple covalent. Let us look at the properties. Y has a low melting point. Wow, low melting point. So we should be thinking simple covalent. So we can put a tick beside that in our minds. It does not conduct electricity. Well, we're still thinking about simple covalent, because we know those do not conduct electricity. And then they said that this is soluble in tetrachloromethane. Even though you don't know what tetrachloromethane is, they say it's an organic solvent. And we know that simple covalent compounds dissolve in organic solvents. And we saw that a few weeks ago when we dissolved our camphor ball or naphthalene in acetone. So tetrachloromethane is an organic solvent, just like acetone. So we know like will dissolve like. So this one would give us simple covalent. So we just have to review revise the structure, the properties of the different structures of the solids that we can have. And then we have this one now. A boy got some copper chloride solution on his shirt. Which will dissolve the green stain better, water or alcohol? Now the question to ask yourself is, what kind of a compound is copper chloride? So if copper chloride, CuCl2. Now we see copper there, which is a metal, chlorine, which is a non-metal. So we know this is an ionic substance. And one thing we know about ionic substance is that they dissolve in water. Ionic substances will dissolve in water. So it means water would be the better solvent with which to use to get out this stain, like dissolves like. So ionic substances dissolve in water, which is very polar. It's a very polar solvent. So the better solvent to use here would be water. All right, and then we're moving on to the parts that you've been waiting for. What is the mass of? So we're going to be doing some conversion. Here we're converting mass. So we're looking at a conversion from moles to mass. What is the mass of 0.5 moles of calcium? And I'm not going to go the formula route. I want us to still use the concept of reasoning. So what is the mass of 0.5 moles of calcium? Now we need to look in the periodic table and find the mass number for calcium. When we do so, we will see that the mass number for calcium is 40. So we know that the molar mass then is 40 grams. So if the molar mass of calcium is equal to 40 grams, this means that 1 mole of calcium is equal to 40 grams. So if we had 0.5 moles of the same calcium, what mass would that be equal to? Of course, cross multiply, we'll end up with 1 mole times X is equal to 0.5 times 40. And 0.5 times 40 will give us 20. So we know that we'll end up with 20 grams being our answer. All right, so let's move on to part B. Part B wants us to find what is the mass of 0.1 moles of sodium chloride. Well, you will not find sodium chloride in the periodic table, but you will find the elements that make up sodium chloride. So you'll find 1 sodium, and if we have 1 sodium, we know that that is 23 times 1, which is equal to 23. You'll find an atom of chlorine, whose mass is 35.5. That times 1 is 35.5. Take the sum of that, and that will give us 58.5. So now that we know that 1 mole, so we're going to say 1 mole of NaCl is equal to 58.5 grams. So if we have 0.1 moles of the same NaCl, that is equal to X. We cross multiply. 1 mole times X is equal to 0.1 mole times 58.5 grams. And we divide both sides by 1 mole to make X the subject. And what we're left with is 0.1 times 58.5 grams, which will give us 5.85 grams. And if we look at that, we're seeing that 0.1 mole, that's like saying 1/10 of a mole. So we'll just take our 58.5 and find 10% of that, or find 1/10 of. No, it is crucial to focus carefully on what the question is asking. Now, in number 5, it is I don't want to say it's a trick question, but what's very important for us to note here is that they ask how many moles. Even though they say of molecules, they're asking how many moles. So this one comes down to a question of moles, and they're given A and B, they ask about grams. So it's moles and mass. So yes, it would be moles of molecules, but they ask about moles. So let's see, they want to find how many moles of sulfur dioxide molecules are present in 10 grams of sulfur dioxide. So of course, what we're going to do, we have to find the molar mass of sulfur dioxide, which is the same as finding its RMM, then expressing it in grams. So you'd have to look in the periodic table for the mass of sulfur, which we will see. So we're looking at SO2, the mass of sulfur, that's 32 for sulfur, 32. It's one of it, so 32 times 1 is 32. For the 2 oxygen that's present, 16 times 2, that's also 32. The sum of that is 64. So we know that the molar mass then, so we'll say the molar mass of SO2 is equal to 64 grams. So in other words, 1 mole of sulfur dioxide has a mass of 64 grams. So that's the statement we will write. We'll write that 1 mole of SO2 is equal to 64 grams. So we want to find out how many moles of the SO2 molecules here would be equivalent to 10 grams. Again, we're going to cross multiply. When we cross multiply, we go across the diagonals. All right. So let me use a little green to show that. So we'll take this and multiply, and we'll say it's equal to what's over here. So that will give us 64x is equal to 1 mole times, well, I shouldn't say 64x, 64 grams times x. Let's be consistent. So 64 grams times x is equal to 1 mole times 10 grams. So of course, to make x the subject, we're going to divide both sides by 64 grams. And there we go. Of course, grams will cancel out grams. 64 grams divided by 64 grams. Grams will cancel out grams. So what we're left with now is 10 over 64. For those who are doing the formula, if you had said number of moles is equal to mass divided by molar mass, you would end up at the same point right here, because looking at this that we have now, we're seeing where it boils down to the mass that you're given divided by the molar mass. So that's 10 divided by 64, and that is 0.16 if we're writing that to 2 decimal places. So that would be 0.16 moles of SO2 molecules. All right, and then we're going to do the same thing for 5B. This is a video, so you can stop, rewind, replay, and take it at your own leisure. So we're given the relative atomic mass of potassium, RAM. In the periodic table, you'll find that as 39. It does not have any unit, it's dimensionless. But we know that if we are asked to find the molar mass of potassium, we would just take this RAM and express it in grams per mole. So the RAM is given, and they're saying, okay, so if the RAM is 39, what is the mass of 5 moles of potassium? So you know that the RAM of potassium, which is K, is 39. It simply means that the molar mass of K is equal to 39 grams per mole. All right, so we could put mole to the -1 to say per mole. All right, so our statement will be this. We will say, okay, 1 mole of K, which is potassium. People tend to mix up that. They tend to write P for potassium, but P is phosphorus. So 1 mole of K has a mass of 39 grams. So we want to find out what's the mass of 5 moles. So we'd say 5 moles of K would be equal to X. And if we're looking at it formula wise, then it's simple. If let's not look at the formula. So we'll end up with X times 1 mole is equal to 5 moles times 39 grams. All right, anything times 1 is itself. So we pretty much will get our answer here being 5 times 39. 5 times 39, 39 times 5 is equal to 195 grams. So if 1 mole has a mass of 39, 5 moles would be 5 times 39. It's like knowing how much 1 dozen represents. So 1 dozen represents 12, 5 dozen would be 5 times 12. So if 1 mole in this case represents 39, because we're talking about mass now, not Avogadro's number. We're concerned about mass. So if we know that the molar mass, the mass of 1 mole is 39, and they want to find out what mass would be represented by 5 moles, we just say 5 times 39. All right. And then we move on to part B of number 6. All right, so we're at B now. We want to find the number of moles that's present in 5 grams of water. And we have worked with water over and over to know that the formula is H2O. It's made up of 2 atoms of hydrogen, 1 atom of oxygen. So when we're finding the RMM, we're going to say we have 2 hydrogens. So it's the mass of hydrogen 1 times 2, which is equal to 2. We have 1 atom of oxygen, so it is the mass of oxygen 16 times 1, which is equal to 16. Take the sum of that and we'll end up with 18. So it means that the molar mass, big M little r as we call it, is equal to 18 grams. Molar mass gives the mass of 1 mole. So we're going to say then, our statement will say 1 mole of H2O is equal to 18 grams, or it has a mass of 18 grams. So we're saying how many moles of water would we have if we had not 18 grams, but if we had 5 grams? So in your mind, you should be thinking now, okay, so 1 mole is 18 grams. So if I have 5 grams, I should have less than 1 mole because 5 is less than 18. So of course, when we cross multiply, we'll end up with 18 grams times X is equal to 1 mole times 5 grams. We want to make X the subject, so we divide by 18 grams. And this is just another way of saying mass divided by molar mass will give us moles, because that's what we have right here. We have the mass that we're given, the 5 grams, being divided by the 18 grams, which make up 1 mole. So we have 5 divided by 18, and that will give us the number of moles of water that's present, and that is going to be 0.28 moles. And I've written that to 2 decimal places. All right. So we're moving along onto number 6. They want to find the number of moles. Don't be intimidated by the number of moles of atoms. Yes, because we're talking about potassium. So the particles there are atoms, but they're asking about the number of moles of the potassium atom that would be in 125 grams. So we'd write our statement again. We would say 1 mole of potassium is equal to 39 grams. So how many moles? X moles of the same potassium is equal to 125 grams. So in essence, we are converting the mass that is given to moles. So when we cross multiply, we'll end up with 39 grams times X is equal to 1 mole times 125 grams. So to make X the subject, we will divide by 39 grams on both sides. And there, what we have is the given mass, 125, being divided by the molar mass of potassium, which is 39. And for those who are thinking formula, that is saying mass given divided by molar mass, 125 divided by 39, and that would give us 3.21 moles, and that's written to 2 decimal places. All right, so that's number 6. So we're moving on to number 7. We're coming down nicely. What is the volume measured at STP of or for 16 grams of oxygen? STP refers to standard temperature and pressure, and 1 mole of any gas or the molar volume of any gas at STP. So we'll say the molar volume of any gas at STP is equal to 22.4 cubic decimeters, dm cube. All right. So we want to know what is the volume measured at STP of 16 grams of oxygen. So, okay, so we're concerned now about volume of gas and mass. So since we know that molar volume is 22.4, 1 mole of the gas would occupy this volume. But we know that 1 mole of any gas also has what we call uh, a molar mass. So we're talking about oxygen. So before we even look at the 16 grams that's present, we know that oxygen is diatomic. Oxygen, anything that ends in gen or in is diatomic. So we would represent it as O2. Okay, so with that in mind, we can figure out the mass of 1 mole, the molar mass of oxygen here. So the molar mass of oxygen, molar mass of the molecule oxygen, O2 would be equal to 16 times 2, which is equal to 32 grams. So this is the molar mass. So the molar mass has 1 mole. So it means that the 1 mole of O2 is equal to 32 grams. We haven't started working it, we're just reasoning our way out. So we're saying then, since molar volume is 22.4 dm cube, we're saying that the 1 mole of the gas would occupy this volume. Now, 1 mole of oxygen is the same as 32 grams. So we'll say 32 grams of oxygen, which is 1 mole, will occupy 22.4 dm cube. And if you look at this, then intuitively you should be seeing that 16 grams of O2 is really half of a mole. So it should occupy half the volume. So intuitively, you'll see that this will work out to 11.2, but we'll put the x and cross multiplying just the same. 32 grams times x is equal to 16 grams times 22.4 dm cube. And of course, we want to make x the subject, so we're dividing by 32 grams on both sides. When we divide by 32 grams, if you look, you'll see that there's a portion of this where 16 is being divided by 32, which is the same as saying half. So we'll end up with half times 22.4, and half of 22.4 is equal to 11.2 dm cube. All right, if you want me to slow down, just stop the video, rewind it, and you should be fine. I think that is it. So the next one, 7b, we want to find the volume measured at STP of 18 grams of nitrogen. Again, nitrogen ends in gen, so we know it's diatomic. We're talking about N2. So the molar mass of nitrogen, you'd have to look in the periodic table to see the RAM of nitrogen. Nitrogen's RAM is 14. So that makes N2 14 times 2, 28. So the mass of N2 would be 28. So the molar mass, 1 mole of N2 is equal to 28 grams. So we know that this 28 grams of N2 would occupy 22.4 dm cube at STP. So if you have 18 grams of N2, naturally it's going to occupy a volume less than 22.4 because 18 is less than 28. So we put x, we'll cross multiply, we'll end up with 22.4 dm cube times 18 grams is equal to 28 grams times x. So we want to make x the subject, so even though it's on the right hand side this time around, but we do the same thing, we divide both sides by 28 grams, so we get x standing by itself. When we do that, we will end up with, well, this will cancel out. Yeah, 28 grams cancel out 28 grams. So we're left with 18 divided by 28. And whatever we get from that is multiplied by 22.4. And that would give us x being equal to 14.4 cubic decimeters. We're talking about volume here, 14.4 dm cube. And look at that, just like that, we are at the last one. calculate the percentage by mass of water in that sodium sulfide with 9 water. So that's hydrated sodium sulfide. So the dot 9 water here is telling us that 9 moles of water or 9 units of water is attached to 1 unit of the sodium sulfide. Na2S. Sulfur is in group 6. So when it reacts, it would accept 2 electrons to make it S2 minus. Cut off the last part of the name and we add IDE, IDE, it becomes sodium sulfide. So we'll have to look at the RAM of the different elements that are present. So the RAM for sodium, we know it's 23. For sulfur, we know it's 32. For hydrogen, we know it's 1. And for oxygen, we know it's 16. So we're going to find the mass of everything that is present. And then we find the percentage by mass of water. So let's check this out. We have 2 atoms of sodium here. So this would be, so our 2 sodium would be, let's see what we get from that. That would be 23 times 2, which is equal to 46. We have 1 unit of sulfur, 1 atom of sulfur. So from that we'll get 32 times 1. That will be 32. And then let's check this out. Now we have 9 water. So we know that the 9 that is here, it means 9 is multiplied. Everything that comes after the 9 is multiplied by the 9. So it means that we'll have, for the hydrogen, we'll have 18 atoms of hydrogen. 9 2 is 18. So it would be the mass of hydrogen, which is 1 times 18, which will give us 18. And for the oxygen, we have 9 of it. 9 atoms of oxygen. So that would give us 16 times 9. And I don't know my 16 timetable so far. I know it up to 5 times 16. So I'm going to have to resort to the calculator for this one. So 16 times 9, let me just double check. Times 9 is 144. I did not know that. Is 144. And what I'll do, I'll just put the part that's associated with water, I'll just bracket it. All right, so 9 water there, 9 water. All right, okay, so let's add everything. So 8 plus 4, 12, plus 2, 14, plus 6, 20. Okay, let's go back in red. So 20. 4 plus 1, 5, plus 3, 8, plus 4, 12, plus 2, 14. And sometimes when I'm adding up, I lose track along the way. So this is 240. All right, so let's just punch these in the calculator to double check. So we have 46 plus 32 plus 18 plus 144, and we end up with 240. All right, so the mass of the total mass of the compound here is 240. So the part of it, the mass of it that's associated with water would be, so the mass of water, you want to find the percentage composition or by mass for water, would have to take the mass of water that's in the compound. So it's mass of water in compound over the mass of the compound and we multiply that by 100 because we're doing percentage. So we know the mass of the compound already. We know that the mass of the compound is 240. So we'll just look at the part, the mass of it that's associated to water, which would be 18 plus 144, which is 162. And that's the same as saying 9 moles of water. 9 times 18, 162. So moving on, we'll end up with 162 divided by 240 times 100, because we're looking at that as a percentage. If you got a test marked out of 240 and your score was 162, your percentage would be 67.5%. All right, so this is it. What I would like you to do is to state, match your answers with what is here. You can just mark your work based on what is here. Which ones did you get right? All right, and you can always give your response. So I hope this has been helpful.
This is where we say copulator. So copulator.